Hello everyone, this is Mrinal Kanti Roy Chaudhary. The title of the talk is An Open Problem on the Quantization for Uniform Cantor Distribution. A homogeneous Cantor set C can be constructed by an iterative function system in many different ways by two similarity mappings. So one of them is S1, other one is S2. S1x equal to Rx, S2x equal to Rx plus 1 minus R, where R lies between 0 and 1/2. The Cantor set C is called homogeneous because the two similarity ratios of the two similarity mappings are same. Let P equal to this. Then P is a uniform Cantor distribution with the support the homogeneous Cantor set C. Graf and Luschke gave an exact formula to calculate the optimal sets of n means and the corresponding nth quantization errors for all positive integers n when r equal to 1/3. Let me now show you their results. And this is their paper, the quantization of the Cantor distribution, where they mention about their results. For a word sigma of length k over the alphabet 1, 2, it is meant this sigma 1, sigma 2, sigma k, which belongs to 1, 2 to the power k. That means there are k symbols which are coming from the alphabet 1, 2. And if we say S sigma, then that means composition mappings, which is given by sigma 1, S sigma 2, like that, up to sigma k. A word of length 0 is called the empty word and is denoted by the null symbol phi. For the empty word p by sp, we mean the identity mapping on R, and write j equal to j phi, which is sp of 0, 1 is 0, 1. For sigma belongs to 1, 2 to the power k, we write j sigma equal to s sigma j. And what is s sigma? Here it is defined. Then C is equal to this one, is known as the Cantor set generated by the two mappings S1 and S2, and equals the support of the probability measure P given by this. Now, I am going to show you explicitly how C is constructed. So our whole interval is 0 to 1, which is J. Now, if you apply S1 on this closed interval 0, 1, then you get 0 to 1/3 interval, which is denoted by J1. And J2 means when you apply the mapping S2 on the closed interval 0 to 1, then you get J2. Now, you see you get these two intervals in the 0th stage, first stage, second stage. In the second stage, you get four intervals. One of them is, they are J11, J12, J21, and J22. Remember, this J11, many people, they get confused in the beginning. They think when you apply S1 on this interval, you get, look, this interval you got from here when you apply S1. This interval you got from here when you apply S2. This interval does not come, look, this interval comes from here, that's fine, but this interval does not come from here when you apply the mapping S2. When you say J11, that means you have to apply the composition mapping S11 on this interval. Then you will get this one. J12 means you have to apply the composition mapping S12 here, S sigma, S12 on the whole interval 0 to 1. Similarly, to get this interval J21, see from J2, you get the 2, 1, 2, 2. You have to apply the mapping S21 on the interval 0 to 1. Similarly, say when you say J122, you have to apply the composition mapping. That means S sigma. Here sigma is 1 to 2 on this interval 0 to 1. Then you will get this one. You will not get it from here. Similarly, for example, say another one, say J2 to 1. So you have to apply the mapping S sigma, which is sigma is 2 to 1 on this interval 0 to 1. Then you will get. See that there is the nicely it is coming with a pattern 1 1 1 2 2 1 2 2 1 1 1. See that from here 1 1 1 1 1 2 1 2 1 1 2 2 2 1 1 2 1 2 2 2 1 2 2 is same. See that then you add 1 then 2 to get the other two intervals and so on. And this is the same. Graf and Lushgi showed that optimal set of one mean is the midpoint. Of course, you can easily guess because it's uniform distribution. And there are also these basic intervals are of equal lengths in each level. So optimal set of two means these 2 points. This midpoint, this midpoint. Optimal set of three means consist of these 3 points. 1, 2, 3. Or 1, 2, 3. That means there are 2 different optimal sets of 3 means. Then optimal set of 4 means 1, 2, 3, 4. Unique. So optimal set of 2 means there's only one. Optimal set of 4 means only one. Similar optimal set of 8 means also only one. But optimal set of like 5 means, 6 means, if it is not 2 to the power k form, you will get multiple optimal sets of n means. That means if n is not of the form 2 to the power k for some positive integer k, you will get multiple optimal sets of n means. Okay. Now, next. The exact formula given by Graf-Lushgi to calculate the optimal sets of n means and the corresponding nth quantization errors does not work for all r 0 to 1 half, 0 to 1 half. Look at that here. Here, this homogeneous Cantor set and r lies between 0 and 1 half. They proved they calculated optimal sets of n means and the nth quantization errors for r equal to 1/3. Their exact formula does not work for all r in this interval. Long time, look, their result was published in 1997. Long time it was an open problem. That what is the least upper bound of r for which the exact formula works. Roy Choudhury gave an answer of it. Let r belongs to 0 to 1 half. R is a number between 0 and 1 half. Be the unique real number such that this relation is true. Then R0, which of course this comes as an irrational number, and approximately after 10 significant digits is this number, gives the least upper bound of R for which the technique given by Graf-Lushgi works. Remember, our R lies between 0 to 1 half, but their formula works up to this much, 0.43. Then what happens to the next? Open problem. Let S1x equal to Rx and S2x equal to Rx plus 1 minus R, where R lies between 0 and 1 half. Then take P equal to this. If their least upper bound we got 0.4350411707. If R lies between from this number to 1 half, then what are the optimal sets of n means and the nth quantization errors for the uniform Cantor distribution P for all n, for all positive integer n are not known yet. So this is an open problem. So long time open problem. And the result, to know more details about this, here is the paper. See, M. Roy Choudhury, number 3. So list upper bound of the exact formula for optimal quantization of some uniform Cantor distribution. It was published in Discrete and Continuous Dynamical System Series A in 2018, like after more than 20 years of Graph-Rutke's result. So I would like to thank you for listening. God bless you.